Can everybody hear me, kind of? Maybe? All right. Trying to figure out where to put this mic. Can everybody hear me, even without it? Kind of? All right. So what I'm going to do is I'm going to go over my review for about an hour, 30 minutes, and then I'll take whatever questions you guys want to go over for the last, 45 minutes or so. I do have these at the end. Remind me, somebody, to pass these out. They're like a quick survey, just to, do whatever. I do have some other problems that I do want to go over, some things that you haven't seen in a while, like combustion and a limiting and things like that, just so you don't forget those. But yeah, so let's go ahead and get started. If I can't see past this podium over here, so just yell out if you have a question on something, and then we'll, I'll go from there. All right. All right, we're going to start out pretty basic because, like I like to say about the ACS test, is it's more of a reading test. So take that how you will. Again, you got to know the concepts. Just read the question, see what it's asking, and then go from there. Okay? All right. So all the following properties are physical properties of matter, except which one? Should be a no-brainer. D, cool. Does everyone agree? Ability to rust, mass, color, melting point, physical properties, observable, ability to rust. Let me put this here. Okay. Which state of matter has a defined volume and takes the shape of the container? B, it's liquid, defined volume, shape of the container. Which of the following is a heterogeneous mixture? Air, salt water, steel, soil. Heterogeneous. It's going to be soil. Steel is a mixture of elements that you can't tell the difference. Salt water, same thing. Air, same thing. Soil, you can pick out the individual pieces. Again, another heterogeneous mixture problem. Which of the following is a heterogeneous mixture? Vinegar and water, milk, oil and vinegar, or air? Oil and vinegar or air? Cool. It says oil and vinegar. Everything else mixes together pretty well. Okay? A substance that can be separated into two or more substances only by a chemical change is a compound. Cool. Only two or more substances by a chemical change, that's breaking a bond. Chemical change is a compound. Which of the following is a chemical property? Ability to react with oxygen. Cool. That's, again, if you see reacting, color, hardness, freezing point, they're all physical properties. All right. The closeness of our measurements to its true value is a measure of its blank. True value. This is the precision versus accuracy. Go back to chapter 1. Which one is it, precision or accuracy? Cool, accuracy. Does everyone agree? Cool, it's accurate. If you're accurate, you're on target. If you're precise, you're in the same grouping. Okay? So if I have a value, if I measure a value and it's 10.1, 10.2, and 10.15, that's precise. If the true value is 9.0. Okay? Because I did the experiment 3 times and I got the same value or very similar values even though the true value is 9. Okay? So true value, accuracy. If the temperature changed by 100 Kelvin, how much does it change in degrees Celsius? What? 100 degrees. Does everyone agree? Cool. So the step of 100 each Kelvin step is the same as a degree Celsius, so it changes by 100 degrees. The particles that are found in the nucleus of an atom are protons and neutrons. Cool. All right. The atomic number of an element is the total number of which particles in the nucleus? Atomic number. Protons, right? Because remember, an element is only an element as long as it has the same number of protons. Different number of neutrons, what is it? Awesome. Isotope, different number of electrons, what is it? Ion. Awesome. Cool. Page 1, pretty simple. Okay. An element has an atomic number of 76. The number, can everybody see this? Pretty good. Right. An element has an atomic number of 76. The number of protons and electrons in a neutral atom of the element are blank. So does anybody have a periodic table? We're looking for number of protons and electrons in the neutral atom. So first, well, it's good to have a periodic table out, so get the periodic table up. So first, we said we have an atomic number of 76. So how many protons do we have? 76. And if we have a neutral atom, is there a charge? No. So is the number of electrons the same or different? So 76 protons, 76 electrons. Okay? Let me zoom in a little bit. All right, it's a little better. The sum of protons and neutrons in an atom equal what? Awesome, the mass. Why don't we count the electrons towards the mass? Awesome, they're very small. How much smaller, so I don't know if this was a quiz question, it might have been. How much smaller are electrons than protons and neutrons? Approximately. I know it was a test question in my Chem 1A class. They're approximately 2,000 times smaller. So that's why they don't count. So, you know. All right, what does number 84 in the name Krypton 84 represent? Anybody know? Mass number. Cool. So that's our mass number. Cool. All right. All atoms of the same element have the same. What did we say before? Protons. Isotopes of the same element have different neutrons. All right. Which of the following sets of symbols represent isotopes of the same element? All right, so what do we have to look for if we're looking for the same element? Awesome, and which number? So if we have an X, we have something up here, something over here, and something over here. What is this number? Awesome, this is protons. What's this? Mass. And what goes here? Charge. So this is a no-brainer. You look for protons, there you go. Okay? All right. Which of the following is a number of neutrons? Which of the following is the number of neutrons correctly represented? Okay? So for number of neutrons, we have protons plus neutrons equals the mass. So mass minus protons equals neutrons. So we have 24 neutrons. That goes away. Let's see. 0 neutrons. That goes away. 75 minus 33 is not 108. What's 238 minus 92? Is that 146? I assume so, because there you go. I probably should have my calculator out, just in case. All right. How does the energy of an electron change when the electron moves closer to the nucleus? Higher energy level, higher, you're farther towards the farther from the nucleus, you're at a higher energy level. Okay? All right, what is the shape of the 3p orbital? Is it a sphere, a dumbbell, a bar, or two perpendicular dumbbells? Dumbbell, cool. So remember, we have, for the quantum, remember we did quantum numbers. We have the S as a sphere, we have the dumbbell as the P, we have the two perpendicular dumbbells as the D, well, bending, and the F's definitely weird. Okay? It also depends where they're oriented. How many sub-levels are in the second principal energy level? So what's our principal quantum number? Awesome. This is our N, is our second. So in the periodic table, which I should have brought mine. I think I have one. I do have one. All right. In our second principal quantum number, how many subshells are there? Sublevels. We have an S and a P, so we have two. The shape, not the size of an electron cloud, is determined by the electrons' length. The shape, not the size of an electron cloud, is determined by the what? Oh, yeah, okay. The shape, not the size. What determines the shape of the electron distribution for quantum numbers? Principal quantum number? Cool. But so within the principal quantum number of 2, what's the shape on the S? It's a sphere. What's the shape on the P? So it's the sublevel. Cool. The letter P in the symbol 4p3 indicates that the spin of an indicates the spin of an electron, the orbital shape, the principal energy level, the speed of an electron. Remember, orbital shape, dumbbell, P. Cool. All right. I'm going to do a different problem. I'm going to diverge from the review for a second. We're going to go to a titration question. I know because those are your guys' favorite. Is it okay if I move this? All right. All right. A 25 milliliter sample of an unknown HClO4 solution requires titration with 22.6 milliliters of a 0.2 molar NaOH to reach the equivalence point. What is the concentration of the unknown HClO4 solution? All right, so what's my first step? Awesome, we got to write a reaction. So what are my two reactants? Awesome, plus NaOH. And that forms what? H2O plus NaClO4. Cool? All right, first step, write the reaction. Second step, to balance. So go ahead and practice for 1 minute. Balance this equation. balanced? Cool. All right, so we have the same numbers of things on the same time, so we have our balanced chemical equation. All right, so now I'm going to rewrite the reaction a little bit neater, actually. Give me a second. All right. So we have our reaction, which was HClO4. What's HClO4's name again? What is it? Awesome, perchloric acid. Does everyone agree? HCl, or what did I do? NaClO4. Cool. All right, that's not neater, but what I like to do is this. All right, so with titration problems, first step, write the reaction. Second step, balance. We're in a balanced equation. Okay, now what I like to do, this doc cam is not very comfortable. Now what I like to do is write down what I know about the reaction, okay? So how much HClO4 do I have? 25 milliliters. Awesome. How much NaOH do I have? 22.6 milliliters. Awesome. What else do I know about NaOH? Awesome. 0.200 molar NaOH. I don't know my molarity. That's what I'm looking for. And do I know anything else? Any other pieces of information given? All right, cool. So now, what can I find out from the volume and the molarity? Awesome, I can find number of moles. So I get moles, or first molarity equals moles per liter. Cool? So I have a 0.200 molar NaOH equals my moles per liter. What's 22.6 milliliters in liters? Awesome. 0.0226 liters. So I can find that moles of NaOH equal, let me do that with my calculator. Times 0.200. I get 0.00452 moles. So now I know I have 0.00452 moles. Okay? I have my moles. So now, can I find my amount of moles of HClO4? Awesome. I use my mole ratio, which happens to be 1 to 1, so this is NaOH. 1 mole NaOH to 1 mole let me just finish writing that. HClO4. It's a 1 to 1 mole ratio, so I get 0.00452 moles of HClO4. Okay? All right, so I went ahead and I converted from moles of NaOH to moles of HClO4. Okay? Are there any questions to this point? So remember, if your equation is not 1 to 1 like this, if there's a 2 here, make sure to do this step to do the mole to mole, your molar ratio, because that's going to change. Okay? All right, now we have moles, 0.00452. 52 moles HClO4. Okay, now can I find my concentration? I'm going to use my formula again. Molarity equals moles per liter. okay? Which is going to equal, I have 0.00452 moles of HClO4 divided by my liters, which I have 0.025 liters, which is going to equal 0.1808 molar. That's how you do a titration problem. Okay, so it's really a 4-step problem. I know it freaks some of you guys out. Step 1, write and balance the equation. Step 2, find your number of moles. Step 3, convert from number of moles of the one you know to ones you don't. Step 4, use your same molarity equation to find your concentration. All right? Any questions on a titration problem? All right, let's do a few more on the review, and then we'll go to a different type of problem. Also, if you wanted to see that a little cleaner, that's there. But you can see that at the end. Okay. Trying to stay somewhat organized. All right. All right, according to the Auftaub principle, an orbital may be occupied by only 2 electrons. Electrons in the same orbital must have opposite spins. Electrons enter orbitals from highest energy to first. Electrons enter orbitals from lowest energy first. Which one is it? Awesome. D. Cool? All right. What is the electron configuration for potassium? So let's go to my periodic table. We're looking for potassium. Okay. Okay, so we have the 1s, 2s, 2p, 6, 3s2, 3p6, 4s, 1. Any questions on electron configuration? So essentially, the way I think of it, potassium's here. I need to go through all the way down to get to potassium. So remember, what is this shell or orbital? S. What's this one? Awesome, this one's the D. What's this one? P. Awesome, and this? F. Cool. So we're going to just go down the line, 1s, 2s, 2p, 3s, 3p, 4s, 1. Okay? If we wanted to do this in noble gas configuration, what's my nearest noble gas to potassium? Argon. So we do Ar, 4s1. Simple? All right. So which one is it? I think it's this one. Yeah, there we go. All right. How many unpaired electrons are in a sulfur atom? Atomic number 16. So let's take a look. Let's do an orbital diagram. Zoom out a little bit. All right, we're looking for sulfur. So let's just do, what's the outermost energy level of sulfur? 3p? Awesome. So it's 3p4. So let's draw the 3p orbital. How many electrons can the p orbital hold? 6. All right, this is the 3p. All right, and you said there are how many electrons in that outer group? So 4. Awesome. So we're going to fill in each box up, 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 and then down. So how many unpaired electrons are there? 2. So is this paramagnetic or diamagnetic? Para, cool. How do you know? Awesome. Para, unpaired, di, 2. Well, you know, they're always together. Okay? All right. How does the speed of visible light compare with the speed of gamma rays when both speeds are measured in a vacuum? Awesome. They're the same. Cool. All right. Which color of visible light has the shortest wavelength? What? Violet? Cool. Violet. So remember, it goes, you know, through the order of colors, starting with red, ending with violet. Okay? Violet being the shortest. Which one has the most energy? Red light or violet light? Violet. Cool. Shorter wavelength, higher energy. Remember all those equations that had a lambda and whatever? You know? That's your relations between them. All right. The light given off by electric discharge through sodium vapor is? Awesome. Emission spectrum. That's how, fun fact, that's how we can look through a telescope and see what things are made of by the light that passes through them. We can see what comes out. All right. Which two categories of elements does an element belong to if it is a poor conductor of electricity? What? Awesome. Non-metals. Metals conduct. Metalloids are a little bit different. They conduct or not conduct. And non-metals don't conduct. Which element has the electron configuration there? So we're going to go, what can we just look at to figure out which is this element? Awesome. We just look for the 3p. This is 3p2. 2p, 3p, 1, 2, silicon. All right. Atomic size is generally, can you guys see this or no? Can you guys see that? All right, atomic size is generally what? What? Cool. So let's decreases when you move left to right. So on this periodic table, which one's the largest? Awesome. Largest. So we could say it increases this way. Cool? Or this way, and down. I suggest if you still don't know the trends, print out one of those ones, just Google periodic trends and look at the image search, and they show all the trends on one periodic table, okay? I'm not even going to read that. It says the answer is D. Cool. All right, what element is in the second period and has the largest atomic radius? Back to periodic trends. Second period, which one's the second period? Here, correct. Second period, which one has the largest radius? Lithium. Cool. Does everyone agree? Just follow the trend. End up with lithium. All right. Let's do another different type of question. Where'd I put it? So we have the reaction PBS, solid, aqueous forms. PbSO4, solid, 4H. All right, which one? Here. All right, so this is an S. Okay. So which one is oxidized? Which one is reduced? So this is a redox reaction. Which one's oxidized? Which one's reduced? And which one's the oxidizing agent? Which one's the reducing agent? Take 1 minute and try to do this. You're more than welcome to talk to people around you. Yeah, PBS. I'm getting a different pen now. So it's better? All right. I have different pens. Okay. All right, so let's go ahead and figure out our oxidation states. So which one do we know here? Sulfur has an oxidation state of what? -2. So what does Pb have to have? +2. All right, do these coefficients matter for redox reactions? No. Don't even worry about them. All right, what is this compound called? Awesome, this is hydrogen peroxide. So in a peroxide, what is the oxidation state of oxygen? -1/2, does everyone agree? -1. It's a superoxide. This is peroxide. Oxygen is -1. -1 times 2, -2. So what does each one of these have to be? +1. All right. Oxygen we know, -2, for a total of what? Altogether, we have -8. Sulfur is going to be what? So let's take a look at the polyatomic, okay? So if we look at the polyatomic here, what's the charge on SO4? 2-, okay? So everything within this polyatomic has to equal 2-. So what does sulfur have to be to equal 2-? It has to be +6. So in order for the whole thing to be 0, what does Pb have to be? Okay? So this is -2 + 6 + 2. All right. And finally, H2O, what's the oxidation state on oxygen? -2. What's the oxidation state on hydrogen? +1. Awesome. So now what you do is you look for change. So what's changing from the left to the right? Sulfur. Cool. So sulfur is going from -2 to +6. All right. And what else? Oxygen. Cool. So what's that mnemonic again? Oil rig. Oxidation is losing, reduction is gaining. So oxidation is losing electrons. Which one's losing electrons? This is oxidation. Which one's gaining electrons? Which one's the reducing agent? Awesome, sulfur. So it's just the opposite. So the agent is, the reducing agent is going to be the one that's oxidized. And which one's going to be the oxidizing agent? Oxygen, which is the one that's reduced. It's causing the other one to be oxidized, causing the other one to be reduced. Okay? Any questions on redox? Yeah. All right, so cool. So with peroxides, okay, so you got to know, well, there's two ways you look at this. First, what I tell students is to do column 1 first, okay? So column 1 is always going to be +1, okay? That's just part of our rules we learned before. Column 1 is going to be +1, so what does oxygen have to be for this to be neutral? 0. Cool. So this is a peroxide. It's called hydrogen peroxide. In peroxides, oxygen is always a -1. All right? Any questions? Other questions? All right, we're making good progress. Let's do one more of these. I'll put it here. Trying to save my paper here. All right. I'm going to zoom in so you can see that. All right, take 2 minutes. Tell me what's oxidized and what's reduced. All right, did everybody try it? Okay. Let's go ahead and go over it. What's P4? Let me zoom out just a hair. What's P4 by itself? 0. Awesome. H? plus 1, O, minus 2. Okay, so H is plus 1, O is minus 2, so we have a plus 1 here, we have a minus 8 total. So in order for this to be equal, or in order for this to be 0, the total oxidation state to be 0, or charge to be 0, what does chlorine have to be? Plus 7. Cool. Or plus 6, 7. 7. Can't do math this morning. Too much football yesterday. Plus 7. What? All right, plus 7. All right, oxygen, minus 2, hydrogen, plus 1. Let's take a look here. Hydrogen is going to be plus 1, plus 3 is total. Oxygen, minus 2, minus 8 total. What does phosphorus have to be? Plus 5. Awesome. All right. And now here we have plus 1, minus 1. Cool? All right, so what's changing? Phosphorus is going from a 0 to a plus 5. And what else is changing? Chlorine's going from a plus 7 to a minus 1. So which one's oxidized? What? Phosphorus, cool. So this is, which one's reduced? And the agents are just what? The opposite. They're flipped. Okay? Any questions? All right. Let's go back to the review. All right, so what I'm going to do is I'm going to skip a page. We're going to resume at 44 because they're pretty much the same thing. You guys can practice. The answers are already posted. The last couple of pages are the answers for them, so you can go over those. So we'll start at 44. All right. And let me grab the paper. Okay, so when placed between oppositely charged metal plates, the region of a water molecule. So, what's the Lewis structure for water? I'll do it here. What's the Lewis structure for a water molecule again? Or actually, yeah, what's the Lewis structure? Two, three, four. Hydrogen. Hydrogen. Is everybody comfortable writing Lewis structures? Yes? No? Maybe? So if I gave you H3PO4 and said write the Lewis structure, could you do it? All right, take 1 minute, do that one, and then we'll resume this question. H3PO4, it's right here. Just want to make sure you're able to write a Lewis structure. All right, let's do H3PO4. What's my central atom? P. What goes around that? Oxygens. What's hanging off those? No, I'll just put it here for, I'll put it there. Hydrogens. Cool. So we have hydrogens all around the oxygens. How many electrons in the outer shells are here total? 1, 2, 3. How many for each oxygen? We have 6. 6 times 4 is what? I can't do math this morning. 24. 24. Phosphorus is what? 7, right? No. 5? 5 plus 24 is 30, or 29 plus 3, 32. 32. 32 electrons. All right. So let's go ahead and place our lone pairs. Yes. Yes, I can. So we have 32 electrons. So how many electrons are in bonds? 1, 2, so 2, 4, 6, 8, 10, 12, 14. Minus 14 electrons in bonds. What do we get? Somebody that's good at math, please help me. 22 minus 4 is what, 18? 18? All right. 18, so let's go ahead and place these 18 electrons. So how many does this oxygen need to be a full octet? 2 lone pairs, cool. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's minus 18, 0. So is everything full on electrons? Cool. There's my Lewis structure for what? All right. What's the name for this compound too? Because if they ask, say, okay, what's the or how many lone pairs of electrons are on the oxygen and phosphoric acid? Okay, you got to know what it is. Now you know the name, but there you go. So you got to remember your names. Meanwhile, naming's very important. All right. Anyway, back to this question. All right. So we had a question: when placed between two oppositely charged metal plates, the region of a water molecule attracted to the negative plate is what? So remember, this was the last lecture he did on, what was it, Thursday? We had our, so which side's the positive? Hydrogen side. Cool. We have lone pairs here. So we have a dipole. Yes. That's a good question. Why? So if you look, when we only place double bonds when we have to. Okay, we have enough lone pairs to make it. So when we do this, that gets rid of one of these lone pairs. But how many electrons does this have? It can, but if it doesn't have to, it won't. Okay, so if you have like PCl5, then it'll make it. But without this, it's just going to make the one with a lone pair. Okay? Does that make sense?
To determine the central atom, as a rule, you just look for the one that's
Awesome.
least electronegative?
Least electronegative besides hydrogen. Okay? Yes? That's a good point. But, so, an expanded octet, avoiding an expanded octet is going to trump a formal charge. Okay? So it doesn't want to expand that octet. It's happy with 8. Noble gas configuration, it's happy with that. If it has a formal charge, so the caveat with formal charges. So if we have a formal charge, for example, I have a question on resonance structures, which we'll get there. It's okay to have a formal charge. So it's okay to have a formal charge. The one that's most electronegative likes to be the most negative, though. Okay? So, but we'll get there. But regardless, it doesn't make this double bond. It has a lone pair here. Okay? Right. Back to the plate here thing. Water molecule, negative plate. All right, so remember we had something called a dipole moment. We went over that a little bit. So we had a positive, kind of drew something like this. We had a positive end here and a positive end here, starting from the hydrogen because we have lone pairs which are very negative. So this side, if anybody's in physics, you sum these two vectors, you're going to have a total dipole moment facing this way. Okay? So this is going to be my negative side. This is going to be my positive side. Okay? So, which one's going to be attracted to the metal plate? The negative plate. So we have a positive plate and a negative plate. And we have our water molecule. And we're seeing what's attracted here. Do negative and negative attract, or do positive and negative attract? Positive. So this hydrogen side is going to. So the hydrogen region of a molecule. Okay? And what's this shape called again? Remember your shapes from, I kind of drew it in the shape. Bent. Cool. So what causes it to be bent? The lone pairs. Lone pairs cause it to be bent. All right? One more question on the water molecule thing. So if I have my water molecule, more water molecule. H, 2 lone pairs. What is the hybridization on the central atom, the oxygen? Okay? Does everybody know what I mean by hybridization? So if we have parking spaces, so I had a chemistry teacher once, he was a little bit nuts. He said, all right, think of a taco stand. Here's your taco stand. That looks terrible. There's my taco stand. I have parking spaces around the taco stand. Okay, so there's my parking spaces. All right? So it's going to take the order. This is my S parking space. This is my P parking space. P parking space. P parking space. D parking space. D parking space. So depending on how many parking spaces are taken up is going to be your hybridization. So how many parking spaces are on this oxygen? 2? Does everyone agree? Do lone pairs take up a parking space? S, P1, P2, P3. Okay? Lone pairs take up a parking space. It's an electron group that takes up the parking space. So this is an electron group, electron group, electron group, electron group. All right? Can I move on from the water molecule? Any questions on hybridization? No. Okay. All right, what type of ions have the name ending in IDE? IDE. Anions? What do you mean? So it says, so the answer choices are up there. Hold on, let me find my sheet thing here. All right. Ending in IDE. Okay, so what's only metal ions, only gaseous ions, only cations, only anions? Awesome. Remember, we replaced the ending to what? With what? On most compounds. IDE, which is the second. So only anions. All right, when naming transition metal ion that can have more than one common ionic charge, the numerical value of the charge is indicated by a what? Roman numeral. Which of the following compounds contains Mn3+? Should be a very 2 seconds. Which one contains Mn3+? C. Remember, we switch charges, or switch numbers, so the 3+, 2-. It's a minus. All right? Which element, when combined with fluorine, would most likely form an ionic compound? Lithium. Carbon, phosphorus, chlorine, all nonmetals, one metal. Which is the correct formula for potassium sulfite? Awesome. Sulfite, C, does everyone agree? What's the charge? So what's sulfite? SO3 2-. Potassium has a charge of what? K plus, 2 minus, plus, SO3, 2 minus. So, see. All right, which is the formula for phosphoric acid? We already did this one. I already gave you phosphoric acid. All right. What does an ite or ate ending on a polyatomic mean? Has oxygen. Make sure that I'm correct. Has oxygen. Okay. Avogadro's number of representative particles is equal to 1 what? Easy, mole. How many molecules are in 2.10 moles of CO2? So let's do this one. I have blank paper somewhere. There we go. Avogadro's number, represented particle, or what am I doing? This one. 2.10 moles CO2. Going moles to molecules. Okay? 1 mole CO2 is equal to how many molecules? 2 times 10 to the 23rd molecules. So, does everybody know the easy way to do scientific notation multiplication? Multiply the front two numbers and then just add or subtract based on what those front two numbers are. So, there's my calculator. I know which one it is, but yeah. 6.022 times 2.1 is going to give me 12.64. 12.64 times 10 to the 23rd, represented in scientific notation correctly, is going to be 1.6264 times 10 to the 24th molecules. Okay? And how many sig figs do I have to report this in? 3. I started with 3, I end with 3. 1.26 times 10 to the 24th. What is the mass in grams of 5.90 moles of C8H18? C8H18. So we have 5.90 moles C8H18. What is my molar mass of C8H18? Somebody? 114? 114 grams C8H18, 1 mole. So 5.90 divided by, or what am I doing? I swapped it. I was like, what am I doing? Man. I promise, I usually don't make this many mistakes. 1 mole C8H18 to 114 grams C8H18. .6 grams. How many sig figs did I start with? How many sig figs do I have to end with? Okay. All right, let's do another different one. Let's do a combustion analysis. Okay. This one. The combustion analysis of a hydrocarbon, CXHY, produces 99.03 grams of CO2 and 40.53 grams of water. Calculate the empirical formula for the hydrocarbon. Okay. So, first step, Write the reaction. CxHy plus O2 forms CO2 plus H2O. All right, how much CO2 do I have? 0.03 grams, 0.3. I don't even know what I'm doing. 99.03 grams, 40.53 grams of water. Okay, so that's what I know. So now I need to figure out where is all of the carbon on this side coming from? From the hydrocarbon. Where's all the hydrogen coming from? From the hydrocarbon. So by the conservation of mass, I can figure out how much hydrogen, how much oxygen came from that hydrocarbon, and then turn it into an empirical formula problem. So let's figure that out. So let's start with carbon. So I have 99.03 grams, okay? 99.03 grams of CO2. Okay. What is my molar mass of carbon dioxide? 44.02, I think. 2 grams of CO2, 1 mole CO2. All right. And for every carbon dioxide, for every 1 mole of carbon dioxide, how many moles of carbon do I have? What?
For every 1 mole, you have 1 mole carbon.
Awesome. 1 mole of carbon. Okay. All right, so I have 1 mole of carbon per 1 mole of carbon dioxide. Now I'm going to take a stop. Actually, I can just end it here. So how many moles of carbon dioxide do I have? I'll do it. 2 moles of carbon. All right, now let's do hydrogen. All right, for hydrogen, I have 40.53 grams of H2O. Okay, what's my molar mass of H2O? 18.02 grams H2O. 1 mole H2O. Okay, for every 1 mole of H2O, how many moles of H2 are there? 2 moles of H. Okay? And when I do that, I get 40 times 2 divided by 18. I get 4.498, 4.50 essentially, moles of hydrogen. All right, now we have an empirical formula problem. So what do I have to do? Awesome. Divide by the smallest number of moles. Smallest number of moles, 2.25. We get 1 carbon. Divide by 2.25. What do I get? 2 hydrogens. So what is my empirical formula? Questions? And what the structure of CH2 looks like. Never mind. We're not going to worry about that, actually. All right. Any questions on this one? I was trying to do something else, but don't worry about it. All right. Let's go back to the review. I'm going to go on the review for another, 10 minutes or so, and then any questions you guys have, more than welcome to ask. Okay. All right. Let me see which ones I want to hit first. All right, we'll go. All right. What volume in liters of 0.500 moles of C3H8 gas, or what is the volume of, what was I saying? What is the volume in liters of 0.5 moles of C3H8 gas at STP? So what are the conditions for standard temperature and pressure? Awesome, 273 Kelvin, 1 ATM. Does everyone agree with standard temperature and pressure? Okay, so what formula am I using? What is it? Awesome, Pivner. PV equals nRT. What gave it away? ATM, moles. Moles. If you have moles, we're going to use PV equals nRT. So what's my pressure? 1 ATM. V, we don't know. Equals N. What's my N? 0.5. What's my R? 8. 2. What is it? 0.0821? 1. And what's my T? Okay. When I do this, 0.5 times 0.08. 11.20 liters. Okay? All right. Next one. What is the percent by mass of carbon in acetone? All right. Percent by mass. So how do we do percent by mass? It's the mass percent. So do we have to go to moles? So how much? Get this. So what is the total mass of C3H6O? Huh? So it's 12 times 3 is what? Plus 16 plus 6. I got it. Plus 16 plus 6. 58? Yes? No? Maybe? 58? Total is 58 grams of CH6O. What's my mass of carbon within that? 36 grams. Cool. So I do 36 divided by 58 times 100. It's going to give me my mass percent. 36 divided by 58 times. It's going to give me 62 point, roughly 62.1%. Okay? Questions on mass percent? It's just the amount of the part divided by the total times 100. All right. What is the empirical formula for a compound that is 40% sulfur, 60% and 60% oxygen by weight? All right. So if we have percentages, what do we assume? Awesome. We just change these to grams. We're going to scratch this out and put a G, because we're assuming we have 100 grams of the substance. Assuming 100 grams. So we have 40 grams of sulfur. What's my molar mass of sulfur? 32.2 grams of sulfur, 1 mole sulfur equals, can somebody put that in the calculator when I set the next one? We have 60 grams of oxygen, 16 grams oxygen, 1 mole equals, can somebody let me know, answer this one? 1.25? And what about this one? What is it? 3.75 moles. Oxygen, sulfur. All right, we're going to divide by the smallest one. Empirical formula problem, 1.25 divided by 1.25. What's this going to equal? 1. This one? So this is 1 sulfur, 3 oxygens. So we have S. SO3. All right. I think you guys can balance, so we'll skip that. All right. The type of reaction that takes place when one element reacts with a compound to form a new compound and a different element is cool. So we have a compound. We have an element and a compound. So this is my element plus my xy. This is my compound, or this is my zy, I guess. Forms xz and y. Single replacement. It's just one partner switching. Okay. All right. Okay. Which of the following is a balanced equation representing the decomposition of lead-4 oxide? So we have lead-4 oxide. We have to figure out what that is. So we have lead-4, Pb4+, oxide, O2-. So we have 2 of these. What am I doing? 4 of those, so we just do 2 of those. Okay? Lead-4 oxide. So we just need 2 oxygens. Forms Pb plus O. All right. So balanced. How many leads do I have on this side? 1. So I'm good. How many so this is O2. And am I good? Okay. PbO2. There we go. All right. Does anybody have that handout with the metal activity series? Otherwise, we'll skip it because I don't remember off the top of my head. Remember that handout he gave with the periodic table? That's a great handout with the solubility rules. Save that. You're gonna want that. It has the solubility rules, has a periodic table, and has a metal activity series. So just look at the metal activity series to see which one's higher than hydrogen, I guess, and then it'll knock it off. All right. If the combustion reaction takes place between rubidium and bromide, the chemical formula of the product is blank, or a combination reaction. So Rb and Br. What's the charge on rubidium? Back to the periodic table. What is it? +1. What's Br? -1. So we just have Rb and Br. Okay? The calculation of quantities in chemical equation is called, this is number 64. Awesome. That's what you guys have been doing all semester. I think you guys can figure this one out. How many moles of aluminum are needed to react completely with 1.2 moles of FeO? So, just do some stoichiometry. Check the time. I'll go for 5 more minutes. Okay. All right. Hydrogen gas can be produced by reacting aluminum with sulfuric acid. How many moles of sulfuric acid are needed to completely react with 15 moles of aluminum? I guess we'll do one of these. All right. Piece of paper. So we have our reaction. And we know we have 15 moles of aluminum. All right, so how do I figure out how much sulfuric acid is needed to completely react? So I have 15 moles of aluminum. How many moles of aluminum are in that reaction? 2 moles aluminum. How many moles of aluminum? How many moles of H2SO4 are required to react with 2 moles of aluminum? 3. 3 moles H2SO4. Okay? And we're looking for the answer in moles. All right? So 15 times 2 divided by 3, 10 moles of H2SO4. Yeah, you're correct. 15 times 3 divided by 2. I may make some mistakes. Thank you for catching it. 22.5 moles. I set it up right, just put my calculator wrong, right? H2SO4. All right. Okay, you guys can figure out the rest of these. When an equation is used to calculate the amount of product that will be formed during the reaction, then the value obtained is called actual yield or theoretical yield. There was a question here. It's not here anymore. Equation is used to calculate the amount of product. Is it the actual yield or the theoretical yield? Awesome. Theoretical yield. Okay. All right, let's keep moving. All right. At high pressures, how does the volume of a real gas compared with the volume of an ideal gas under the same conditions? Real gas versus ideal. So let's go into the difference, since I know you guys have 10 or 15 questions on here. We'll get back to this in a little bit, but let's go to the difference between a real gas and an ideal gas in a real gas versus ideal gas. So what's the difference between a real gas and an ideal gas? Cool. So when we have a gas, let's say we have gas A and gas B here, or whatever, gas molecules. If a gas, the gas molecules are going to pass by each other. Okay. So what causes what causes a pressure? Okay. A pressure is caused by the collisions on the container of the gas molecule. The smaller you make it, the more collisions that happen, the more force that's expanded outward. Okay? So, with an ideal gas, we don't take into account the attractive forces or the repulsive forces between the molecules. Because what's around, so let's say a common gas, I don't know, whatever. Let's say water vapor, I guess, because it's easy. It's easy to see. Water vapor. Let's say this is water vapor. We're in a gas phase. Okay, we're compressing this. When this water vapor passes by this water vapor, what happens? Cool. The positive, negative dipoles are going to attract to each other depending on their orientation, but also the negative dipoles they're going to be attracted to each other. Cool. So we don't take that into account. Some gases are repulsive to each other. Some gases are attracted to each other. So we don't take, not really. They're attracted to each other. So we don't take into account the forces of attraction and repulsion between the gases. Okay. So that's the difference between an ideal gas and a real gas. So that's why, I don't know if he got to it in a lecture. Did he get to like the real gas approximation with the two constants, alpha and beta? So with the real ones, you put in the approximation. So there's a coefficient per gas that we put in to approximate those forces, and that's in your textbook, you know, in chapter, which chapter is this? Chapter 10? Chapter 5, chapter 5. In chapter 5, so I suggest, so my suggestion for the exam, okay, since you do have these 10 or 15, I think it's 15, right? These 15 questions, is to go over in the back of the book those questions. You know, I like to do the first 2 and the last 3 of each of the sections, because the first 2 are usually the easiest and the last 2 are usually the hardest. So, last 2 are usually the hardest, so I do those, and then that gives me time, you know, if I can't get one of the first 3, then I keep going down the list. So if I get it, then I don't have to do all of them. All right? All right. I'm going to take your questions now. All right? Any questions you have from your quizzes, your tests, any book questions, whatever you want. Yeah. The difference? You don't take into account the attractive or repulsive forces between the gases. Okay? And we use that ideal gas equation, PV equals nRT, because it simplifies. It gives us a pretty good approximation. All right, questions? Textbook, whatever. I can pull up more gas problems if you want. Gas problems, I have a worksheet. I'll pull that up. All right. So also, I will say, if you're struggling with some of these concepts and whatnot, Khan Academy does a very good job of explaining the different concepts and whatnot. Very good. All right. Okay. I'm just going to write it since. So let's say, I'm going to write it. Mixture of H2 and 3.3 moles of oxygen. Uh, 3.3 moles of oxygen gas. A 250 liter container at 273 Kelvin. The total pressure of the gas is 0.75 atm. So what is the partial pressure? What are the partial pressures of the gases? Okay, so this says, I know my handwriting's not the best, especially when I'm writing quick. Zoom out a little bit. All right, so we have a mixture of H2 and O2 gas. The mixture contains 6.7 moles of hydrogen gas and 3.3 moles of oxygen gas. The mixture is in a 250 liter container at 273 Kelvin. The total pressure of the gas is 0.75 atmospheres. What is the partial pressure? Okay, So what do we have to figure out now? What formula are we going to use to figure out partial pressure? Awesome. We're going to use PV equals nRT. What gives it away? Moles. We're given moles, so we're going to go ahead and use PV equals nRT. So let's start with hydrogen. Hydrogen is 2 gas. Okay? All right, what do we know about hydrogen gas? Mixture contains 6.7 moles of H2. All right, and we already said we're going to use PV equals nRT to figure out our partial pressures. So we're looking for pressure. So P. What's my volume? What? Awesome, we have 250 liters. So how do we know it takes up the whole container? Awesome. Gases take up their whole container. They consume the whole volume. So we approximate they assume the whole volume instantly of the container. Equals N. What is my N for H2? What? Awesome. My N? Moles. 6.7. I thought you said 0.7. 6.7 moles. And R, what's my R? 1. And my T? Okay. pH2 equals, so if I have, let me put this in the calculator, 0.0821 times 273. What do I get? Awesome. 0.60. Actually, I made a mistake copying the problem for this. This should be a, no, this will be okay. We'll leave this. 0.60 ATM. Awesome. So now, do I have to do PV equals nRT to figure out the oxygen? Awesome. I'm just going to subtract it from the pressure we already know. The total pressure is given. So, let me just make sure. Yeah, all right. So we already know, or for oxygen, O2 gas, we're going to do our total pressure, which is what? 75 ATM, minus my pressure for hydrogen, which is 0.60 ATM. So what's my pressure for oxygen? 5 ATM. So there are my partial pressures. Questions? Yeah.
If we were to calculate for O2, we would just replace the 6.7 in H2 6.3 multiplied by R times.
Yep. Is it a different answer? Because I copied down the question wrong. This should be 300. Okay. This should be 300. And this will give you 0.5. Should give you 0.5 and then 0.25, I think. Yeah. This should be 0.5 and this should be 0.25. Or ATM. All right. Yeah, I made the mistake copying down the problem, and then I rolled with it. All right. Partial pressures? All right. Any other types of questions you want me to go over? I'll pull any up. So the only thing they can make harder with this is they don't give you the total pressure. You ask for the total pressure the individual pressures, and they give you more than 2 gases. They can give you 3 or 4 gases. Okay? Any other questions? Totally open to go over whatever. I can pull up a few more questions. I'll go ahead and do that. Oh yeah, we can do a bomb calorimeter problem. That's great. Oh, also, I have another review for, so my review for my Chem 2040 students, they're only being tested on Chapter 6 for their final. So I'm doing a whole in-depth Chapter 6 review at 3:30 today. But I can pull, yeah, I'll definitely pull that up. I got that somewhere in my stack of papers here. Somewhere here. Not that one. Here we go. This is a good bomb calorimeter problem too. Okay. A 0.500 gram sample, we're going to do number 3 here. A 0.500 gram sample of TNT is burned in a bomb calorimeter containing 610 grams of water at an initial temperature of 20 degrees Celsius. The heat capacity of the calorimeter is 420 joules per degree Celsius, and the heat of combustion of TNT is 3374 kilojoules per mole. Using this data, calculate the final temperature of the water and calorimeter once the reaction is complete. Okay, so this is a little bit different. Bomb calorimeter problem, we can do a more standard one if you want. Or do you want to do this one? All right, we'll do this one. Okay, so when we're using a bomb calorimeter, what formula are we using? Q equals cat. Cool. Q equals cat. But, so let's say, we have our tank here. Okay, so the heat capacity for the empty tank is 420 joules per degree Celsius. And you already said Q equals cat. C delta T. All right, so this is the empty. This is the C cal empty. All right. And I know I use 610 grams of water to fill it up. So how do I find the heat capacity of that 610 grams of water? Cool. So the specific heat of water, so the specific heat is 4.184 joules per gram times degrees Celsius. Okay? Specific heat. Can I add this to this? This to this. No, but how many grams of water do I have? 610 grams of water. Grams cancel with grams. And I'm left in the same units, joules per degree Celsius. So I find the heat capacity for that amount of water. So when I do that, I get 4.84 times 610. Okay? And that becomes 2552.24 joules. What am I doing? joules per degree Celsius. Okay? All right, so now how do I find the total heat capacity for the empty calorimeter and the water in it? I just got to add them together. So 420 joules per degree Celsius plus 2552.24 joules per degree Celsius equals 2972.24 joules per degree Celsius. All right? And now we can just Q equals cat. We're looking for the final temperature of the calorimeter. Okay? We already have the initial temperature, so Q. What's my Q for this reaction? It's given. 3374 kilojoules per mole. Okay. So we're given, I'm trying to make both of these visible at the same time, that TNT has a molar heat of combustion of 3,374 kilojoules per mole. Okay. How many, so we know in this reaction that we have 0.500 grams of TNT. Okay. So is this my Q for my reaction, or my Q for my calculation here? So this is saying it releases this many kilojoules per 1 mole of TNT. Do I have 1 mole of TNT? No. I don't have 1 mole of TNT. I don't even have close to 1 mole of TNT. So I got to figure out how much heat is released based on my amount of TNT. So that means I got to convert this to moles to figure out how many moles of TNT I have. So TNT is C7H. Can someone help me calculate the molar mass of TNT, which is C7H5N2O6. So 12 times 7 plus 5 plus 14 times 2 plus 16 times 6. Is it already given? No. No. What did you get? 213? All right, let me try this. 263? 213, 213. All right, I'll go with 213. Regardless, it's the same process, so. All right, so if I assume this 213 grams of T, can you see that? Nope. Come on, you guys got to tell me that. You can't, can't let me just do stuff without you seeing it. TNT, 1 mole TNT. All right, 1 mole TNT. All right, so how many moles of TNT do I have? .002347 moles of TNT. All right, so if I have .002347 moles of TNT, that's weird. Moles of TNT. And I know for every 1 mole of TNT, it releases 3,374 kilojoules. How many kilojoules does it release with that many? kilojoules. Okay? And I'm going to go ahead and convert this to joules. There's 1 kilojoules per 1,000 joules. 7920 joules. Now I can Q equals cat this. So I have my Q, just 7920 joules, equals my C, which I already calculated was 29. This is joules per degree Celsius, times, how do I find delta T? Temperature final minus my temperature initial, which is 20.00 degrees Celsius. And now you solve. So if I do divided by 2972 plus 20, I get 22.66 degrees Celsius as my temperature final. Everyone agree with my work? Are there any questions on this one? So this is a little more in-depth bomb calorimeter problem. Usually it's like, okay, what's the molar heat of combustion? This one you're working backwards to figure out the change in temperature. Okay? All right, it is 12:13. I am going to pass out these surveys. I'm going to walk around asking for any questions you guys have. But other than that, I do have another review today for just Chapter 6 for my Chem 2040 students. You're welcome. I'm going over, that's this one. It's all of Chapter 6. So, you know, everything helps. I don't know, here's a bunch. Yeah, just pass this around. Sure. I'm tired. I'm so tired.